Dear colleagues, today we discuss the possible future developments of composites and mechanics of materials. So, what is the future of composites and materials mechanics? And what the society expects of us? One thing, structures must be reliable. They should serve and remain intact for many years, and not break. So simple it is. Composites are on the market since 1930s. Lord Kelvin once said, that there will be no new discoveries in physics. It was 115 years ago. Are all the structural materials problems solved now? No more that problems of physics at the time of Lord Kelvin. Over last years, new tools and ideas appeared, which opened the path to new generations of composites. It is nanotechnology, multi-scale design of materials, computational testing, biocomponents, multiphysics. Let us look around, at the nature. Nacre is 3,000 times more tough than its constituent. Bones are tough, strong and light. Biomaterials have extraordinary properties and have hierarchical, multi-scale structures. Let us look more closely at the role of hierarchy in wood strength. Every scale level represents a composite, controlling different aspects of deformation and strength of wood. Can we transfer and exploit the idea of hierarchical materials in structural composites? Yes, we can. Adding nanoparticles into the composite enhances the fatigue resistance of the material. And it adds additional functionalities, like sensing function. For instance, we carried out experiments. Carbon nanotubes were introduced into carbon fiber epoxy laminates. We observed that the toughness increased by 50%. This work was carried out in a framework of Danish-Chinese collaborative project. Now, how can we choose optimal structures of materials? Can we design optimal materials? We can use computational, virtual testing of materials. Taking into account real structures of the materials, one can generate computational models, using for instance finite elements, and test them in virtual experiments. Here is an example. Crack growth around glass fibers in a composite, observed in the simulations. This rather simple simulations show the main features of computational testing of composites. It includes the analysis of typical structures, and determination of nanoscale properties, idealization and discretization of the material structures, defining the representative element of material, dealing with nonlinear effects. Carrying out the computational testing of materials structures, one can predict the material's performance, and develop recommendations for the material's optimization. These methods can be applied to the optimization of composite structures. For instance, hybrid composites with glass and carbon fibers ensure the reduced weight, and higher strength of wind blades. Are computational simulations allowed to predict the strength and lifetime of such composites? Another example, crack growth in a polymer reinforced by graphene platelets, or by carbon nanotubes. We simulate the crack propagation in various structures. From the simulations, one can make an interesting observation. The shape and type of nanoparticles determine the damage mechanisms in nanocomposites. Graphene nanoscale reinforcements lead to the crack deviation, while long carbon nanotubes bridge the crack. What can we learn from such simulations? We can see how the material structure influences strength. We can predict performance of new materials. And find ways to optimize the materials. For multi-scale composites, computational modeling and testing are much more challenging than they are for common materials. Here, you can see the simulations of crack growth in hierarchical graphene reinforced composites with carbon or glass fibers, and polymer matrix. Fatigue resistance increases drastically when the matrix is nano-reinforced. The strongest effect is when the graphene platelets are localized on the fiber matrix interface. And here, hierarchical composites with carbon nanotube reinforcements. Here, we compared the effect of nano-reinforcements in composites with glass, carbon, and hybrid fibers. The strongest positive effect is for glass fibers. These simulations demonstrated that hierarchical nanomodified composites show much higher lifetime than common composites. Further, their compressive strength is much higher as well. Another important advantage of hierarchical composites is the multifunctionality option. Composites with introduced nanocarbon particles can be used as sensor network, sending the information about deformation and damage of materials to the user. The conductive embedded network can be also used to protect the material from icing and lightning. Another promising direction is the development of nano-engineered coatings, for instance, for the wind blade protection against leading-edge erosion. But how far are hierarchical materials from practical applications? Not too far. First, natural materials. In our recent project, we demonstrated that wood, as a natural composite, can be used for small wind turbines. Our partners in Nepal built a number of such wind turbines, also in schools. In several projects, it was proven that carbon nanotube or graphene reinforced wind turbine blades are economical, and show better lifetime, than common composites. A group from the Case Western Reserve University, in Cleveland, manufactured and tested the carbon nanotube reinforced polyurethane wind blades. It is worth to remember. Wind turbine materials are in fact the forefront of development of structural materials. Cars can be repaired. For wind blades, it is difficult. Airplanes can be expensive. Wind turbines must be cheap, to be competitive. Thus, new solutions for wind turbine materials lead also to new solutions for lightweight cars, airplanes, ships. Let us look at the market perspectives of composites. Both the markets for composites in general, and for wind turbine materials are expected to show remarkable growth in next 5 years. In Sandia Laboratory, materials are one of 4 main areas in the wind energy program. Industry needs new better materials. Summarizing. The future of composites lies in the development of hierarchical, multifunctional, nano-engineered materials. Mechanics, first of all, computational mechanics, is the tool to design and optimize the composites. A few words about myself. I am senior researcher at the Technical University of Denmark. Before coming to Denmark in 2005, I was working at the University of Stuttgart, and have got my habilitation degree at the Darmstadt University of Technology. Here, you can see some references to our works. If you have questions, feel free to contact me via this email. Thank you very much for your attention.